Today we're going to look at some of the review problems for the final exam. Here they are. I'll just kind of get them started and I'll let you finish them. On 1A, suppose I want to calculate the circulation, which is also the same thing we calculated called work. If F is x squared for its components, how do I calculate that with Green's theorem? We'll see the path counterclockwise around the boundary of the region enclosed by y equals x, the line splitting the axes, and y equals x squared, the parabola. Well, we can find these intersection points by setting these two curves equal, right? Where they intersect, their y coordinates are equal, so x equals x squared says that x equals 0 or 1. So this is where the region between these two curves begins and ends. Now, if we're traversing this counterclockwise along the boundary of this region, and that's our curve C, what is the value of this line integral, which if F is a velocity field can be interpreted as circulation, if F is a force can be interpreted as work. Well, we'll say that by Green's theorem, this is the double integral over the region R enclosed, dF2 dx minus dF1 dy, where F1 and F2 are the components of F. Or sometimes it's written dg dx minus dF dy with little letters. dA. Well, let's see, F1 and F2 in this case are both the function x squared. So this is the double integral over the region of 2x minus nothing. How do I integrate over this region? Well, I can make it either a vertically simple or horizontally simple region. Let's integrate it. X going from 0 to 1, we're more familiar with the vertically simple region. So it's bounded on the left by x equals 0, on the right by x equals 1. And now the bottom curve is y equals x squared. And the top curve is y equals x. So we integrate from x squared to x. 2x dy dx. Well, this is integral from 0 to 1. X squared, I'm sorry, not x squared, 2xy evaluated at x squared and x. All right, I'm integrating with respect to y, treating x as a constant. And so I put in x and I get 2x squared. I put in x squared and I get 2x cubed. So what I have here is the integral from 0 to 1, 2x squared minus 2x cubed dx. And let's see, this is then 2x cubed over 3 minus x to the 4th over 2. Plug in 0, 1 and take the difference. It's 2/3 minus 1/2. It's 1/6. Well, this next example asks us to use a line integral to find an area. Remember, that was a special application of Green's theorem. There were 3 different formulas. One of them was that you could evaluate area as integral x dy. This was a corollary, if you like, of Green's theorem. Or you could put minus y dx, or you could add both those together and divide them by 2. Let's do this one, the simple one. Area is integral x dy. So, to integrate along the boundary, taking counterclockwise, if you go clockwise, you'll get minus the correct result, right? So, we can evaluate the line integral using our theorem that says if you integrate a function in here, dy, you replace x as a function of t, dy with dy dt dt, and maybe I should put that way, x of t. Let t run over its range. Well, t goes from 0 to 2 pi. X is 5 cosine t and y is 5 sine t. Is the way you can write the circle parametrically of radius 5. So we'll integrate from 0 to 2 pi. And for x, we'll replace it with 5 cosine t. For dy, we'll replace it with dy dt, 5 cosine t dt. Now I have to integrate, pulling the 25 out, cosine squared, which remember the trick there is to just use the half angle identity and say cosine squared is 1 plus cosine 2t over 2. When I integrate this, integral of 1 half is 1 half t. Integral of 1 half cosine 2t is 1 quarter sine 2t. Plug in 0 and pi and take the difference, you get pi out of this, so the answer here for the area is 25 pi as expected. The next problem is Green's theorem for multiply connected region. Here's a region with a hole in it, right? For multiply connected regions, as long as you keep the region on your left on each curve, on C2, the region's on my left, on C1, the region's on my left, which means the inside curves you have to go clockwise, and the outside curves you have to go counterclockwise. The line integral over the union of these curves is equal to the usual Green's result, double integral of df2 dx minus df1 dy over the region. That's what we have here. So this line integral plus this one must be equal to the double integral over the region enclosed. There's Green's theorem for a multiply connected region. So now we say the problem also tells us that the line integral around C2 is known to be 40. So we'll put that in. And that over the region df2 dx minus df1 dy is equal to 2. So we'll put that in. Well, now this is the double integral over the region of 2. If you take the 2 out, integrate 1, the integral of 1 is the area, so this is just 2 times the area. And we have line integral around C1 plus 40 is twice the area of R, the region between these two curves. Well, that region's area is easy to calculate. It's a 6 by 3 rectangle with a radius 1 circle cut out. So its area is 6 times 3, 18, minus pi r squared. Pi times 1 squared is pi. And when you do the subtractions, you then find out that the line integral around C1 is minus 4 minus 2 pi. If you get a problem similarly, or similar to this, and C1 goes the other way, what do? You just rewrite the theorem as this one minus this one plus this one equals this one, right? Because this integral, taken the other direction, just changes its value by minus. So the integral clockwise is minus the integral counterclockwise. For the vector field F, with components 2x and 4, if we travel along a curve through that field, given with this position vector, t, 2t squared for components, t running from 1 to 2. Suppose we also look at the scalar field, f of x, y, just a function, is x squared plus 4y. Verify that this vector field is the gradient of this scalar function. Well, we just do the gradient as the vector of partial derivatives. So gradient of f of x, y, where f of x, y is x squared plus 4y, is just d dx of this followed by d dy of this. That's all the gradient is. Partial with respect to x of x squared is 2x, of 4y is 0 because y is treated as a constant. Partial of x squared plus 4y, you treat x as a constant when differentiating with respect to y. Take the derivative of 4y is 4. So that comes out to be precisely capital F, which shows that capital F is the gradient of little f. Now, to evaluate the line integral along a curve, since the vector field is conservative, the gradient of some scalar function, we can evaluate the line integral simply by plugging in the final point to little f minus the initial point. In other words, little f is a potential, and the fundamental theorem of line integral says that to evaluate a line integral of this vector field, you can take the potential at the final point minus the potential at the beginning point and get the value without actually having to do the detailed definition of line integral. So this is f of 2, 8 minus f of 1, 2, since the curve, xy is t, 2t squared. When you plug in 1, you get 1, 2. When you plug in 2, you get 2, 8. So we need the potential at 2, 8 minus the potential at 1, 2, which comes out to be 27. Next, let's look at this problem. Evaluate the scalar line integral of little f equals 3x minus 2y along this curve. Given parametrically x equals 2 plus t, y equals 2 minus t, t running from minus 2 to 1. I'll remind you there are two types of line integrals. This was the vector line integral, integral f dot dr. The scalar line integral is just the integral of a function, ds, along some curve c. So if c is given by position vector r of t equals 2 plus t, 2 minus t, t running between minus 2 and 1, we'll say that this line integral is equal to 3x of t minus 2 y of t square root of dx dt squared plus dy dt squared. dt is how this can be evaluated. The ds becomes length of r prime of t dt. And now t runs from minus 2 to 1. So this is going to be the integral from minus 2 to 1 of, let's see, 3x of t is 3 times 2 plus t, plus 2 times y of t is 2 minus t. Square root of dx dt is 1, dy dt is minus 1. And I just have to do this simple integral from minus 2 to 1. 6 minus 4 gives me 2. 3t plus 2t gives me 5t. And then the square root of 2 here I can pull out. dt. And that will evaluate the scalar line integral. Now let's try a vector line integral. A vector line integral is the integral f dot dr of a vector field along a curve. For this particular one, with a vector field that has components x squared, xy, and I traverse the quarter circle in the fourth quadrant clockwise. That's this one right here. I go from 1, 0 to 0 minus 1 along the curve x squared plus y squared equals 1. Remember, we can write that path parametrically as x equals cosine t, y equals sine t if we're going this way. If we put x equals cosine t, y equals minus sine t, we traverse it this way. And we can let t go from 0 to pi over 2 because it is actually the clockwise polar angle now. So we'll integrate. Remember that we can write the integral f dot dr when we can't apply Green's theorem and we can't apply the fundamental theorem of line integrals. We go to this one. We say that it's the integral f dot dr dt dt evaluates this line integral. Well, f has components x squared, xy, so it's cosine squared, cosine times minus sine, x squared, xy, for the parametric form. dr dt is the derivative of these components, minus sine t minus cosine t, and we just have to evaluate this integral. Well, dot product this times this plus this times this is actually 0, so we're integrating 0 along the path. In fact, this line integral is then equal to 0. Now suppose we want to sketch the domain and express the iterated integral in the opposite order. Recall that sometimes that made the integral easier to do. Here's my double integral, iterated integral. I'm integrating x going from 0 to 1 and y going from 0 to 1 and x going from y squared to square root y. What you do on these is first draw the picture. If y is on the outside, then this means this is the minimum y, this is the maximum y. Those are always just numbers. So y goes from 0 to 1. On the inside, you can have functions of y, and I'm integrating with respect to x, then between this curve on the left, x equals y squared, and this curve on the right, x equals square root y. So I've sketched those, x equals y squared on the left, and x equals square root y on the right. The bottom one's on the left, top one's on the right, and that is for each y, I go from here to here, and I sweep out this region. Now, once you've sketched this, you can, in this horizontally simple form, you can try and write it in a vertically simple form. X goes from a min to a max. Well, since these intersect at x equals 1, x goes from 0 to 1. And then I want to go from a bottom curve to a top curve, so now I draw the line here. On the bottom is this one, which is x equals square root y. But now I have to write y as a function of x, so I square both sides and find y equals x squared. That's the bottom curve for this vertically simple reason. And on the top here, x equals y squared, I square root the sides and get y equals square root of x. And so now we go from bottom curve, y equals x squared, to a top curve, y equals square root of x running from a min of 0 to a max of 1. Now suppose you have an integral like this that's nasty, because when you evaluate this in the inside integral, it's hard to integrate in the outside integral. This one is better done in polar coordinates, so I said change the polar coordinates and evaluate it that way. Again, this is the min x and the max x, and then y goes between a bottom curve, y equals 0, and a top curve, y equals square root 1 minus x squared. So when you're going to change the integration, first thing you do is sketch the region. This is a vertically simple region. I'll go x from the min to the max, and then this will be the bottom curve, y equals 0, and this will be the top curve, y equals square root 1 minus x squared. Well, what does this look like? If we square both sides, we see it's y squared equals 1 minus x squared, or x squared plus y squared equals 1. It's an arc of a unit circle, right? So we draw the quarter unit circle up above this interval, and the straight line y equals 0 down below it. And here's our region here. Now that we've sketched the region, we can figure it in polar coordinates. To go over the same region, in polar coordinates, we want to go between a ray, theta equals some constant. In this case, it's evidently theta equals 0 radians. And another ray, theta equals, in this case, pi over 2. And between those rays, we want to go from an inside curve. Well, we go all the way back to the origin, so the inside curve is r equals 0. And an outside curve in polar coordinates. Well, it's a unit circle, so its equation is r equals 1. So r in polar coordinates goes theta between 0 and pi over 2, r between 0 and 1, and constant endpoint. It is much easier. Now we have to integrate 3xy, so we put the integrand in terms of polar coordinates. 3 times x is our cosine times theta times y is our sine theta. The y and the x get replaced with r dr d theta, the little area element for polar coordinates. Now the nice thing about this one is since you have constant endpoints, it's easy to work with this. 3 comes out of everything because it's a constant. Sine theta and cosine theta are constant within the r integral, so you can pull them through into the theta integral out here. And once you pull them out here, the remaining part, 3r cubed dr, integrated from 0 to 1, constant endpoints is just a constant. So you can pull the integral 3r cubed dr out of the theta integral, and what you have in the product, 3 times the integral from 0 to pi over 2 of sine cosine, times the integral from 0 to 1 of r cubed. And I'll let you finish it. Now in 2c, you want to use a triple integral to evaluate triple integral of x dv. If w is a solid, x squared plus y squared less than or equal to 1, and minus 4x squared minus 4y squared less than or equal to z less than or equal to 0. How can I do that? Big key is the sketch. Here's the integral I want to evaluate. If I want z between minus 4x squared minus 4y squared and 0, I first sketch the surface z equals minus 4x squared minus 4y squared. Well, I know that this is an upside down circular paraboloid. Right? It looks like this, just from our quadratic surfaces. Z equals 0 is a plane, and what I want, and then x squared plus y squared equals 1, if I put equals on this one, is a circle in the xy plane. In 3 dimensions is therefore the right circular cylinder that extrudes that circle up and down to create this cylinder. So I want to be inside the cylinder, below this plane, and above this circular paraboloid. Once I see that picture, now I know how to integrate it. To do a triple integral, what you can do, our theorem says, you can do the double integral over the region of projection, which evidently is this circle of this disk. Double integral over the disk of the integral z going from the bottom surface, evidently the circular paraboloid, to the top surface, the plane. So I'll go from z equals this to z equals this, bottom surface to top surface. Double integrate the region it projects onto. Well, the region it projects onto is easy to describe in polar coordinates, that is cylindrical coordinates when you also include z. R going from 0 to 1 and theta going from 0 to 2 pi. You replace x with r cosine theta, dA becomes r dr d theta, and we have this integral to evaluate, which isn't too bad. Oh, one more thing. Minus 4x squared minus 4y squared, since I'm going to do cylindrical coordinates, I'll write that as minus 4r squared. Next up, let's try this problem in spherical coordinates. Suppose I want to do the triple integral of x squared plus y squared over the volume of this region of this solid here. X squared plus y squared plus z squared less than or equal to 4. Again, a big key is being able to draw the picture. So you look at what is x squared plus y squared plus z squared equals 4. We recall that's the equation for a sphere of radius 2, right? X squared plus y squared plus z squared equals r squared. So we draw a sphere of radius 2, and we think about what does that look like in spherical coordinates. Well, that's all points at a distance 2 from the origin. Its equation is rho equals 2, or you could say this is rho squared. So this equation in spherical coordinates is rho squared equals 4, or rho equals 2. Since we don't consider rho negative, it just sweeps out this. Now, to integrate over the sphere in its interior, what can we do? Well, we have to write it with, the only way we had for our problems was let theta be on the outside, go between two fixed values, phi go between two fixed values, and rho go between an inside surface, rho 1 of theta and phi, and an outside surface, rho equals rho 2 of theta and phi. Well, here you can go all directions, so you let theta go all the way around from 0 to 2 pi, and then phi go all the way up to down 0 to pi, and you just have to not go more than 2 units from the origin, so you let rho go from 0 to 2, and you have this integral, 0 to 2 pi, 0 to pi, 0 to 2, sweeps out the whole sphere. Now, x squared plus y squared, you can replace these directly with, right, x with rho cosine theta sine phi, y with rho sine theta sine phi, square them and reduce it, or you can recognize that this is r squared in cylindrical coordinates, and r was rho sine phi, so this is rho sine phi squared. This integrand is just rho squared sine squared phi. That's the easiest way to do it, is to go to r and then to x and y, but it works either way. So this is the new integrand in spherical coordinates. And dv has to get replaced with rho squared sine phi, d rho, d phi, d theta, the little volume element dv in spherical coordinates. Now, since we have constant endpoints, another wonderful thing happens, and the functions in here are a product of a function of rho times a function of theta times a function of phi. We can slide these apart, and the d theta could slide straight through because all this stuff evaluated inside is a constant, right? It's evaluated at constant endpoints, so it'll be a constant. We just pull the d theta right through and take integral from 0 to 2 pi d theta. Similarly, we can slide these sine cubed phi out of the first integral and take the d phi through and write this as integral sine cubed phi d phi. And then that leaves the integral of rho to the fourth d rho. These are each easy integrals, right? This one's 2 pi. This one can be evaluated by rewriting it as 1 minus cosine squared times sine, right? 1 minus cosine squared is sine squared, so this is sine cubed. Now you substitute u equal cosine phi, and this will be minus, if you put the d phi here, this will be minus d phi, and you can evaluate this one by a u substitution, u equals cosine phi. this one, it just gives you rho to the fifth over 5. Plug in 0 and 2, it's easy to evaluate also. Well, we said we could find volumes using triple integrals. Suppose I want the volume below the surface 2x plus 2y plus z equals 2. I told you it's a plane, but I'd like you to recognize that whenever you have ax plus by plus cz equals d, that's always a plane, as long as a, b, and c aren't all 0. So what's the volume below the plane within the first octave, right? The first octave is where x, y, and z coordinates are all positive. So I draw the plane. I can sketch this plane 2x plus 2y plus z equals 2 by simply making a table. I can put in x equals 0 and y equals 0, and then I find z equals 2, right? I can put in x and z equals 0, and I find y equals 1. I can put in y and z equals 0, and I find out 2x equals 2, x equals 1. So I plot those 3 points, and then I draw the little triangle in the first quadrant here. And I notice that consequently the region of projection in the xy plane is this little triangle here, going out to 1 on the x-axis and 1 on the y-axis. So now I know from our theorems that to evaluate, first the volume is the triple integral of 1 dv, recall that. And to evaluate the triple integral, I can do the double integral over the region of projection R of the integral from the bottom surface to the top surface. Well, the bottom surface is obviously z equals 0. The top surface, I just need to write this, solve for z, is 2 minus 2x minus 2y. So I integrate from the bottom surface z equals 0 to the top surface z equals this, double integral over the plane region xy space. Well, what's that plane region? I can find the equation of this line readily, right? Its y-intercept is 1, so if I put y equals mx plus b, then b has to be 1. And then its slope is minus 1 because I go down 1 and over 1, so it's minus 1 times x plus 1. The equation is y equals 1 minus x. This is the top curve. The bottom curve is y equals 0. So on the double integral, y goes from bottom curve to top curve, 0 to 1 minus x. X goes from min to max, 0 to 1. Here's the triple integral. I need to evaluate the volume. It's just tedious after that. Here's how to find the centroid of a plane region. It works similarly for volumes, you just have to do volume integrals. Find the centroid of the plane region between the curves y equals x squared and y equals 1. As always, it helps you to sketch the region. Sketch y equals x squared, the basic parabola. Y equals 1, the horizontal line. Evidently, this is the region we want the centroid of. Don't waste your time. When you want a centroid, it's just the center of mass for lamina here, a plane region, of uniform density. So if I think about it, where would I balance this thing? Well, right here in the middle, because this side balances this side. So you just write down immediately x bar equals 0 by symmetry. All right. Now I want the center, I want the centroid. Then I also need y bar. I need x bar and y bar. To find y bar, I first need the area of the plane region, right? I can do that as a double integral of 1, right? Area of a plane region is double integral of 1. And if I think of this as a vertically simple region, x goes from a min of minus 1 to a max of 1. Bottom curve y equals x squared. Top curve y equals 1. I just have to evaluate this integral. It comes out to be 4/3. Then I compute the moment of mass using density function 1. That's what this is. Area is really the mass using density function 1. You compute mx is exactly the same integration, just put y in there. And this gives you the moment of mass, if you will. And so you integrate this. I didn't do the details. You evaluate that integral, and that's mx. And then the y bar, the center of mass, or in general, or in this case the centroid, since you're taking density 1, is just mx over a. If you're finding the center of mass, you take mx over m, where you put the density function in here. So this is just mx over a, whatever you calculate here, over 4/3. Oh, suppose we want to find arc length. That means we take the integral ds, or ds is the length of r prime dt. So that's the arc length. It's the integral of r prime of t dt. which is also square root of dx dt squared plus dy dt squared dt. And we have to integrate it, t going from the beginning of the path to the end. If we're given it's the arc of the circle here, 2 cosine t, 2 sine t, t running from 0 to pi over 2, then we replace dx dt with minus 2 sine t and dy dt with 2 cosine t. And we wind up in here with 4 sine squared plus 4 cosine squared, which is 4, and its square root is 2. If we integrate 2 here, we just get 2t. Plug in pi over 2 and 0, we get 2 times pi over 2. Wouldn't you know, in math class, the answer is pi. Suppose instead I want an arc length parameterization of a curve. Here's the curve, r equals 3 sine 2t, 3 cosine 2t, and t for components t running between 0 and pi. Let's say this we've got the curve. So this is actually a circle of radius 3 that we're sweeping out. How do we rewrite this circle, 0 less than or equal to t less than or equal to pi, with an arc length parameter, s? Well, we compute the arc length, remember, by integrating from a to b, r prime of t dt. If we start the curve at 0, then we'll say the arc length from 0 to any time or value of parameter t is just the integral from 0 to t. Here's the arc length from the 0 position to the t position along the circle. Now, the length of r prime is the root sum squared of the derivatives. It's this one derivative squared plus this one derivative squared plus this one's derivative is 0 squared. In 3 dimensions, we have 3 components root sum squared. But this all just reduces to 6. Right? Cosine squared plus sine squared being 1. So we have to integrate 6, and we find out that we get 6t is the arc length along the curve. So once you find the arc length parameter as a function of t, you invert it to find t as a function of s. Very easy in this case. T is 1/6s. And just plug in t of s for t in the original vector parametric form. So I replace s with 1/6t in each component, and then I wind up with this vector, 3 sine t over 3, 3 cosine t over 3, 2, is the position, r written as a function of, should have been 1/6s, sorry, s, as a function of the arc length parameter, s. There it is. Suppose instead I want an arc length parameterization of a curve. Here's the curve, r equals 3 sine 2t, 3 cosine 2t, and t for components t running between 0 and pi. Let's say this we've got the curve. So this is actually a circle of radius 3 that we're sweeping out. How do we rewrite this circle, 0 less than or equal to t less than or equal to pi, with an arc length parameter, s? Well, we compute the arc length, remember, by integrating from a to b, r prime of t dt. If we start the curve at 0, then we'll say the arc length from 0 to any time or value of parameter t is just the integral from 0 to t. Here's the arc length from the 0 position to the t position along the circle. Now, the length of r prime is the root sum squared of the derivatives. It's this one derivative squared plus this one derivative squared plus this one's derivative is 0 squared. In 3 dimensions, we have 3 components root sum squared. But this all just reduces to 6. Right? Cosine squared plus sine squared being 1. So we have to integrate 6, and we find out that we get 6t is the arc length along the curve. So once you find the arc length parameter as a function of t, you invert it to find t as a function of s. Very easy in this case. T is 1/6s. And just plug in t of s for t in the original vector parametric form. So I replace s with 1/6t in each component, and then I wind up with this vector, 3 sine t over 3, 3 cosine t over 3, 2, is the position, r written as a function of, should have been 1/6s, sorry, s, as a function of the arc length parameter, s. There it is. Here's one, draw a contour map showing at least 3 level curves. This is like a topographic map you see of a mountain. What does this function look like? Z equals 9x squared minus 4y squared. Well, maybe you remember from your quadratic surfaces, this is actually a hyperbolic paraboloid. If you forget, you can do some traces and figure it out. Put z equals a constant, you get a constant equals this is a hyperbola. Put x equals a constant, you get z equals a constant plus a constant times y squared is a parabola. Put x equals a constant, you got a constant here, z equals 9x squared plus a parabola. So this is a parabola up, these were parabolas down, a hyperbola is the other way, hyperbolic paraboloid, right? You can kind of guess it. It is the hard one to draw though, it's the saddle shape. It's got its seat centered on the origin since we didn't translate it. It's in its standard form pretty easily. So it looks kind of like that in x, y, z space. Now what we really wanted was level curves. In other words, if we intersected with this with horizontal planes, suppose I intersect this with a horizontal plane. It looks like I'm going to intersect this in some sort of a hyperbola with these two branches. And sure enough, if I put z equals 1 in the equation here, I get 1 equals 9x squared minus 4y squared. Rewritten as 1 equals x squared over a third squared minus y squared over a half squared is a hyperbola with a equals a third and b equals a half. It's this branch and this branch here. So k equals 1, I get these two traces, and then the level curves are the projections of the traces down on the xy plane. So here's the trace for k equals 1. Now I put z equals 0 or k equals 0, thinking of this as function of xy equals k. That's a horizontal plane, that's the xy plane. And within here, I actually intersect in two lines that intersect at the origin, because z equals 0 gives me 0 equals 9x squared minus 4y squared. And then you get 4y squared equals x squared, or y equals plus or minus 3 halves x by square rooting that. So it's these two lines of slope plus or minus 3 halves through the origin. And then I put z equals minus 1. I similarly get this equation, except with minus 1 on the left, which translates to y squared over a half squared minus x squared over a third squared equals 1. That's a parabola, a hyperbola, opening up and down, going through these vertices at plus or minus a half on the y-axis. So here's the level curve here. If I were to intersect with a plane z equals minus 1, I'd get a hyperbola opening the other direction, something like this. Anyway, project all those those traces into the xy plane. We call these the level curves. Here's 3 level curves here. Well, suppose you're asked to calculate the directional derivative in the direction of r prime at the given point to the surface. So in the direction of the tangent, as you move along this curve, r of t equals secant t tangent t, which incidentally is a hyperbolic, right? If you take this squared minus, this squared minus this squared, you get 1 by the Pythagorean identity. And so it's a hyperbola, actually. That's beside the point. We can draw it if we want, but for this one I won't need to. Let's just say if I want to take the directional derivative with this surface, z equals x squared plus 4y squared, in the direction of r prime, then I need first to compute the point of tangency. I compute the directional derivative is the gradient of f dot u. So this is to be memorized. The directional derivative, duf, is gradient f dot u, where u has to be a unit vector in the direction that you want to find the slope of the tangent line. So that's the directional derivative. It's the slope of the tangent line of the surface, z equals f of x y, in the direction of unit vector u. So first I'll find the gradient of f, so I can evaluate this. The gradient of f is just the vector of partial derivatives, 2x and 8y. Now I want the gradient at the point where I'm finding the derivative, so I now replace x, since I'm moving along the curve secant t tangent t, I'll replace x with secant t and y with tangent t. And so gradient of f is just this vector, 2 secant t, 8 tangent t. And at the point where t equals pi over 4, that's where we're finding the slope of the tangent line. So I put in pi over 4, get secant is square root 2, and tangent is 1. So there's the gradient of f at the point in question. Take the vector of partial derivatives, put it in terms of t, and plug in t equals pi over 4. Now I also need the unit vector in the direction I want the tangent. So well, that's supposed to be in the direction of r prime, so I compute r prime by taking the derivative of secant t is secant tangent, derivative of tangent is secant squared. Then at pi over 4, this is square root 2 and this is 1, so I get the vector square root 2, 2 for r prime. That's the direction I want to move. But I need a unit vector, so I divide it by its length, and I come up with 1 over square root 3, square root 2 over square root 3 is the direction I want to move, and it's a unit vector. Now I'll take gradient of f that I computed up here, dot the unit vector, the direction I want to move, and I get this slope of the tangent plane. This times this plus this times this is the dot product, gives me 10 square root 2 over square root 3, or so your algebra teacher doesn't roll over in his or her grave, rationalize it as 10 square root 6 over 3. Well, let's try this. Let's find the equation of a plane that passes through a particular point and is parallel to this particular vector. Whenever you want to find an equation of a plane, think, if I have a point and I have a normal vector, I can use the point normal formula to find it. So what's a point on this plane? Oh, there it is. I've given it in this case. 3, 4, minus 2. What's the direction? Well, it has to be parallel to x minus 2y plus z equals 0. That means it's normal vector when you have x plus by plus cz plus d equals 0. The normal vector, a normal vector, has components that are these coefficients, 1, minus 2, 1. So I want a plane that has this normal vector, and this point, I just use the point normal form, and I say a times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0. There's also vector formulas if you prefer, where this is a, b, and c, and this is x0, y0, z0. You just have to plug those in. You've got 1 times x minus 3 minus 2 times y minus 4 plus 1 times z plus 2 equals 0. You want to multiply that out and get x minus 2y plus z. That's a 2, not a z. Let's see, minus 3 plus 8 is 5. 7 here, so we have minus 7 on this side. So you can write it in this standard form. Well, this problem of finding global extrema is a very long problem, so I'm going to do it in brief. To find the maximum and minimum values of this function over this region, first let's sketch the region. X greater than or equal to 0, that's this half plane. Y greater than or equal to x, that's this half plane over the line y equals x, and y between 0 and 3 is this strip through here. So we have to be on this side of this line, on this side of this line, and between these two, it's this triangle right here. Now what you do to find global extrema is you find the interior critical points where the partial derivatives, both of them are 0, they're candidates, and you find critical points along the boundary by considering along these functions of one variable. You can write the boundaries as function of one variable parametrically, finding the critical points using calculus 1. So the interior critical point, and then check them all. You find the interior critical points, the boundary critical points, plug them all into the function. The largest is the absolute maximum, the smallest is an absolute minimum, because every absolute maximum and minimum of a continuous function on a closed bounded region like this occurs either at an interior critical point or a point along the boundary, which you can find the critical points for also. So, interior critical point sets both partial derivatives to 0. Partial derivative with respect to x is 2x minus 2. Partial derivative with respect to y is 2y minus 4. That says there's only one way you can satisfy both of these, x equals 1 and y equals 2. That's the point 1, 2. There's only one interior critical point. Boundary critical points are long and tedious. I've told you it's a long problem. you can write each boundary parametrically. For instance, along C1, right here, x is equal to 0 and y equals t is a good way to parameterize this little line segment, t going from 0 to 3. So I'll do that. Now, this thought of as a function of one variable, g of t is f, evaluated as a function of x of t and y of t. This parametric curve is a function of one variable. G, the height z over this plane, as a function of t as you move along the boundary, is then f of 0t, since x is 0 and y is t put in, is, let's see, t squared plus 0 minus 2t minus 0. Let's see, did I get that right? Oh, I'm sorry, y is t. 0 squared plus t squared minus 2 times 0 minus 4 times t is t squared minus 4t. So that's g of t. Now to find the critical points along this boundary, I said its derivative equal to 0. Derivative 0 equals 2t minus 4. I find t equals 2 is the critical point along this boundary. Now, also an endpoint, right? At an endpoint, you want to set the derivative to 0, and also at an endpoint is a critical point of the boundary. I'll just put all three corners here, 0, 0, 3, 3, and 0, 3. Then I'll just have to check the interior critical points along the boundaries. So along this boundary, I get one critical point at t equals 2. Well, that's the point 0, 2, right? So there's a point I have to check. I have to check the interior critical point, this interior critical point along the first boundary, these corner points. Let's look at the second boundary, y equals x. Here I have x equals t, y equals t is a good way to parametrically write that, t going from 0 to 3. So this time you take a function of one variable, g of t is f of x, y is tt from the parametric curve, is now, let's see, t squared plus t squared minus 2t minus 4t, and I get 2t squared minus 6t. To find the interior critical points along this boundary, I said its derivative equal to 0. The derivative here is 4t minus 6, so that means t has to be, square root 3 halves, that should be 3 halves, shouldn't it? T has to be 3 halves. And therefore, the point 3 halves along that boundary is a critical point, halfway up there. All right, so let's just put this one here also. See why you check your answers? Right? Now, that's the other lesson for today. Now, finally, along C3, we can put y equals 3 and x equals t, do the same thing. We get one critical point interior to that boundary, 1, 3. So now we have to check the interior critical points of the plane region, the interior critical points along, that's 1, 2, interior critical points along the boundary, 0, 2, 3 halves, and 1, 3. Then we have to check the endpoints of the boundary, 0, 0, 3, 3, and 0, 3. So we plug all those into the function. We know there is a maximum and minimum because it's a continuous function on a closed bounded region. And we just plug those points in. The largest is the absolute maximum, the smallest is the absolute min. It turns out, if you plug them all in, I didn't finish, I got tired. The smallest that you get is minus 5. That occurs at the point 1, 2, the interior critical point. And the largest you get turns out to be at the origin. The maximum is 0. For the last problem, let's try finding a maximum and minimum of a function, x squared y to the 4th, subject to a constraint, x squared plus 2y squared equals 6. We can use the Lagrange multiplier method for such a problem. I'll rewrite the constraint as x squared plus 2y squared minus 6 equals 0, so it's to the form gxy equals 0. Then the Lagrange multiplier method says that the gradient of f, the function to be optimized, has to be equal to lambda times the gradient of g, where the gradient is the vector of partial derivatives. So partial derivative of this is 2x times y to the 4th, that's partial derivative with respect to x. Partial with respect to y is 4x squared y cubed. So we get this vector as the gradient. Gradient of g is easier, 2x, partial with respect to x, that has to multiply I. Should have written this as a vector, I guess. Let's write it that way. Lambda times 2xi plus 4yj is the gradient of g. And then for two vectors to be equal, their components have to match. So 2xy to the 4th has to be equal to 2x lambda. 4x squared y cubed has to be equal to 4y lambda. And we want to keep the constraint. This gives us two equations and three unknowns. Generally, it's not easy to find the solutions, and we can narrow them down a lot by also applying the constraint. Now we've got 3 equations and 3 unknowns. Let's see if we can solve them. This is tricky at this point. It's tempting to divide through by x and say, well, lambda has to be y by 2x. You get lambda equals y to the 4th. Divide through here by 4y and get lambda equals x squared y cubed, y squared, and solve that, and you do get some solutions. You get plus or minus square root of 2, plus or minus square root of 2, but you don't get all of them. What you now have to do is say there's another case. It could be, for instance, maybe lambda is 0 in both these cases. Then x and y, either x or y has to be 0 to make the sides match, right? And that means if x is 0, then I plug that in the constraint, I find out that y has to be plus or minus square root of 3. If y is equal to 0, then I find out x has to be plus or minus square root of 3 to, so if y is 0, x is plus or minus square root of 6. And so you get these 4 points on top of it. Consider all the 0 cases, you wind up with these sets of 8 points, 2 here, 2 here, and 4 here. Now what you can do is plug these into the function, providing it has a maximum and minimum, which you have to be careful of. Then it occurs at those points. Well, I know it occurs there because this is a little ellipse in the xy plane. This is a continuous surface, right? It's just a polynomial surface, whatever it looks like. It doesn't look like this, but what you're doing is you're tracing out this curve. You're thinking of this mountain and finding the maximum and minimum. As you move along this trail on the mountain, it's a continuous function over a closed-bounded continuous curve. You're going to get a maximum and minimum on this thing. So you know it exists just sort of from kind of picturing what these kind of things look like in your head. So you just plug in all these points. The largest is the maximum, the smallest is the minimum. You find out the maximum of 8 occurs at these points. The minimum of 0 occurs at these points. I really need you guys here to correct my minimum of 0.